The observable universe extends outward in every direction as a single continuous region filled with galaxies, radiation, and matter that move according to the known laws of physics. It forms a sphere defined not by any physical boundary, but by the distance that light has been able to travel since the earliest detectable moments of cosmic history. In this region, space expands steadily, carrying galaxies away from one another, while preserving large-scale patterns that scientists measure to understand its structure. Light from distant galaxies arrives after travelling for billions of years, carrying information about how the universe looked at earlier stages. Although these galaxies move through vast distances, their collective behaviour forms a coherent domain governed by gravity, radiation, and the distribution of matter. This domain represents the starting point for understanding any larger theoretical framework by offering a clear and measurable foundation. Within this region, the behaviour of galaxies reveals the presence of forces that act across cosmic distances. Galaxies cluster into groups and filaments due to gravity, forming a network that stretches across space. Despite the complexity of these structures, the overall expansion of space continues uniformly on the largest scales. The expansion determines how far light can travel, setting the limit of what can be observed. These observable limits do not reflect an edge, but rather signify the maximum distance from which light has reached Earth since the earliest detectable period. Beyond this distance, the universe continues, but its contents cannot be observed directly because the signals have not yet had time to arrive. This distinction between observable limits and physical boundaries forms an important part of understanding the universe as a measurable scientific domain. Radiation fills the observable universe in the form of relic light left from early cosmic conditions. This radiation permeates space uniformly, containing subtle variations that reveal how matter distributed itself when the universe was young. Scientists measure this radiation to understand large-scale patterns and to infer properties such as the density of matter, the rate of expansion, and the presence of forces acting throughout the cosmos. Within the observable region, these measurements remain consistent, allowing researchers to build models that describe how the universe evolves. These models rely on the assumption that physical laws operate uniformly throughout the observable domain. Evidence collected from distant galaxies supports this uniformity, showing that matter behaves similarly across vast scales. The observable universe also includes regions where matter exists in states shaped by temperature, pressure, and radiation environments. Dense clusters of galaxies form strong gravitational regions, while voids contain lower densities of matter and radiation. These variations occur naturally within the observable range, representing the distribution of cosmic structures without implying any difference in underlying physical laws. Even where matter becomes extremely dense, such as within galaxy clusters, the overall behavior remains consistent with the fundamental laws describing gravity, light, and particle interactions. This consistency forms a foundation for exploring deeper models without departing from the measurable universe. The expansion of space continues as time progresses, increasing the distances between galaxies while allowing new regions to enter observational reach as light from them arrives. Although the observable universe grows over time, the growth reflects the arrival of signals rather than any shift in the underlying content. This continuous expansion influences how structures evolve. Distant galaxies appear to recede faster than closer ones due to this expansion, and their light stretches as it travels, shifting to longer wavelengths. These stretched wavelengths carry information about the conditions of the early universe and its evolution through time. At these scales, the observable universe behaves predictably. Matter follows gravitational pathways while radiation travels across expanding space. Temperature variations in relic light reveal patterns that match models of early cosmic processes. The distribution of galaxies across different scales follows statistical patterns predicted by these models. Taken together, these observations show that the observable universe forms a coherent domain where known physics describes both structure and evolution. This region does not include assumptions about unobserved realms. Instead, it focuses entirely on measurable behavior. As scientists examine the observable universe, they use instruments to detect radiation across the electromagnetic spectrum. Telescopes collect light from nearby stars and distant galaxies, allowing researchers to reconstruct the arrangement of matter across space. Measurements of cosmic radiation offer insight into conditions present when the universe was much younger. These observations help refine theories that describe the large-scale behavior of the cosmos. The observable domain provides an anchor point for scientific models, ensuring that theoretical frameworks remain grounded in empirical data, even when exploring ideas beyond direct observation. The understanding of the observable universe also depends on how time influences measurement. Light from distant galaxies shows how they appeared billions of years ago, offering a view into earlier cosmic stages. As light from these galaxies continues to travel, it reveals increasingly distant regions. This process means that the observable universe contains a mixture of structures at different evolutionary stages. Some galaxies appear young while others appear fully developed. These differences reflect the time it took for their light to arrive. Despite this variation in apparent age, the underlying physical laws connecting these systems remain consistent. The outer boundary of the observable universe expands as cosmic time increases. This expansion allows more distant signals to reach Earth, adding new information to scientific understanding. The boundary expands not through movement of matter, but through the arrival of radiation from regions previously beyond reach. This distinction matters because the observable limit depends on time rather than on properties of space itself. The horizon does not represent a physical edge but a temporal one. Everything within this region forms part of the measured universe, while everything beyond remains unobservable at present. Because the observable universe represents a region limited by the travel of light, it forms the largest scientifically grounded framework from which researchers explore deeper theoretical questions. Understanding this domain requires recognizing both its scale and its limits. It includes all matter and radiation detectable at present, all large-scale structures revealed through observation, and all interactions measured through physical laws known to operate across cosmic distances. It does not include claims about what may lie beyond. Instead, it offers a complete and coherent foundation for describing the universe as it is observed today. With this outermost region described, the exploration moves inward to examine the structures that fill the observable universe and form the next layer of understanding, where galaxies, clusters, and filaments shape the cosmic environment through which matter and radiation move. Across the observable universe, matter arranges itself into large-scale structures that extend over vast distances and create the cosmic framework through which galaxies and radiation travel. These structures form through the action of gravity acting slowly over cosmic time, drawing matter into patterns that persist even as space expands. The largest recognizable feature is the cosmic web, a network of filaments containing galaxies and clusters that connect across enormous spans. Between these filaments lie wide regions of lower density known as voids, where far fewer galaxies appear. Although these structures differ in density and shape, they all behave according to the same physical laws that govern the motion of matter and the evolution of cosmic environments. This region of structure forms the next layer within the observable universe, revealing how matter organizes itself on the largest scales accessible to measurement. Galaxies gather into groups and clusters bound together by their mutual gravitational attraction. These clusters contain many types of galaxies and vast amounts of dark matter, which exerts gravitational influence without emitting light. The presence of dark matter becomes clear when scientists measure how galaxies move within clusters. The speeds observed require more mass than visible matter alone can provide. This additional mass shapes the structure of clusters and influences how galaxies interact within them. Despite its invisible nature, dark matter behaves predictably within the cosmic web and contributes to the formation of filaments that link clusters across space. These filaments channel matter into structured pathways, creating patterns that reflect the outcome of gravitational evolution over billions of years. Between clusters and filaments, large voids extend quietly across the observable universe. These voids contain far fewer galaxies, yet they remain integral parts of the cosmic structure. Their low density results from the same gravitational processes that build dense regions elsewhere. As matter flows toward filaments and clusters, these voids expand gradually, reducing the number of galaxies within them. The behavior of voids reveals how matter moves on large scales and provides insight into the long-term evolution of cosmic structure. Although voids appear empty compared to clusters, they still contain diffuse gas radiation and dark matter distributed sparsely across space. These regions help define the contrast between dense and diffuse areas that characterizes the cosmic web. The formation of these large-scale patterns began when the universe was young. Slight variations in density present as small fluctuations in early cosmic radiation provided the seeds for structure formation. As time progressed, gravity amplified these fluctuations, drawing matter into denser regions and leaving other areas more diffuse. Over billions of years, these processes created the filaments, clusters, and voids seen today. The distribution of galaxies within this structure provides evidence of how matter moved in response to these early fluctuations. Because the formation of structure follows predictable physical laws, scientists use these patterns to test models of cosmic evolution and to understand how matter behaves on the largest scales. Within filaments, galaxies form long chains that stretch across cosmic distances. These arrangements reveal how matter flows through space, moving along pathways created by gravitational interaction. Galaxies within filaments experience forces that guide their motion, pulling them slowly toward nearby clusters. Over time, this motion strengthens the structure of the cosmic web. Some galaxies merge with others, adding to the mass of larger systems, while others maintain stable orbits within the filament environment. These interactions occur gradually, shaped by the large-scale gravitational field generated by dark matter and ordinary matter combined. Clusters sit at the intersections of filaments, functioning as nodes within the cosmic web. These nodes contain hot gas that emits radiation detectable by telescopes, allowing scientists to measure the mass and structure of each cluster. The hot gas indicates that galaxies and matter within clusters move at high CEU speeds, creating conditions where gas becomes heated through collisions. These temperatures provide insight into the gravitational potential of clusters, revealing how much mass they contain. Observations of cluster environments help reveal how matter accumulates and how structure evolves over time. Galaxies themselves vary in form, ranging from spiral structures with rotating disks to elliptical shapes containing older stars. Their distribution across filaments and clusters reflects both local and large-scale conditions. Spiral galaxies often appear in less dense regions of filaments, while elliptical galaxies appear more commonly in cluster environments where interactions between galaxies occur more frequently. These differences arise from the processes that shape galaxy evolution under the influence of gravity, gas dynamics, and radiation. Despite their differences, all galaxies share a common origin in the early distribution of matter across the observable universe. The cosmic web also influences the path of light travelling across space. As light moves through these structures, gravity bends its path slightly, an effect known as gravitational lensing. This bending allows scientists to map the distribution of dark matter by observing how light from distant galaxies distorts as it passes near clusters or dense filaments. These distortions reveal the invisible mass shaping the large-scale structure, confirming that dark matter plays a central role in forming the cosmic web. The measurement of gravitational lensing strengthens the models of large-scale structure and provides further insight into how matter organizes itself throughout the observable universe. The growth of structure continues today as matter flows slowly through filaments toward clusters. Although expansion stretches space, the gravitational attraction within filaments and clusters remains strong enough to retain galaxies and draw new ones inward. Over long intervals, these processes may shift a mass distribution across the cosmic web, changing the appearance of clusters and altering the density of voids. Despite this evolution, the observable pattern remains dominated by the large-scale network established over billions of years. This network determines how galaxies move and how matter collects, forming the underlying architecture of the universe accessible to observation. Understanding the cosmic structure provides a foundation for exploring deeper scientific models that describe the forces governing the universe. The next inward layer examines the physical laws that shape this structure, focusing on the constants and interactions that determine how matter, radiation, and space behave throughout the observable domain. Across the observable universe, the same physical laws operate uniformly, guiding the motion of galaxies, the behavior of particles, and the evolution of cosmic structures. These laws define how matter interacts with radiation, how gravity shapes large-scale patterns, and how forces influence the development of everything contained within the measurable cosmos. By examining these laws, scientists can describe the behavior of the universe with remarkable consistency, showing that galaxies billions of light-years apart follow the same principles that govern nearby systems. This layer focuses on these fundamental laws as they apply across the observable domain, forming the framework through which deeper theoretical ideas later emerge. Gravity governs the movement of matter on the largest scales. It influences how galaxies orbit within clusters, how clusters gather into filaments, and how the cosmic web forms through the amplification of early density fluctuations. Gravity acts between all objects with mass, and its influence becomes stronger as masses increase or distances decrease. In the observable universe, gravity appears consistent across all measured regions, producing motions that agree with predictions of physical models. The role of gravity becomes especially clear when observing galaxies that move within clusters at speeds requiring more mass than visible matter can provide. These observations suggest the presence of dark matter, which exerts gravitational pull yet emits no detectable light. The existence of dark matter shapes the formation and evolution of structures throughout the observable domain. Electromagnetism plays a critical role across many scales by governing how charged particles interact, how radiation travels, and how atoms and molecules form. Light travels across the universe following electromagnetic principles, carrying information about the distant past. At smaller scales, electromagnetism binds electrons to atomic nuclei and determines how matter emits or absorbs radiation. These interactions create the spectra used to measure the composition of stars and galaxies. Across the observable universe, electromagnetic processes appear to operate identically, producing the same atomic signatures regardless of distance. This uniformity allows scientists to study cosmic conditions across vast scales without encountering differences in fundamental behavior. Two additional interactions, the strong nuclear force and the weak nuclear force, influence processes inside atomic nuclei. The strong nuclear force binds protons and neutrons together, while the weak nuclear force governs certain types of particle decay. These forces shape the formation of elements in stars and during early cosmic conditions. The distribution of elements measured in distant galaxies matches predictions based on these interactions, indicating that fundamental physics remains consistent across the observable domain. These forces operate at scales far smaller than atoms, yet their influence shapes large-scale behavior, because the formation and evolution of stars depend on them. Physical constants define the strength of these interactions. Constants such as the speed of light, the gravitational constant, and the charge of the electron set the framework through which physical laws operate. Observations across the observable universe show no measurable variation in these constants. Their stability ensures that physical models remain accurate when applied to distant galaxies or to early cosmic conditions, because constant values shape the evolution of stars, galaxies, and radiation. Even slight variations would produce observable differences. The absence of such differences across large scales supports the view that fundamental constants remain uniform throughout the observable universe. The behavior of radiation provides additional insight into physical laws. Light emitted by galaxies shifts to longer wavelengths as space expands, a phenomenon known as redshift. This shift reflects the stretching of light waves due to the expanding universe. Measurements of redshift allow scientists to determine the distances and velocities of galaxies, creating a detailed picture of the cosmic structure. The relationship between distance and redshift follows predictable patterns based on known physical laws. These observations confirm the consistency of the electromagnetic behavior across the observable domain. Matter and radiation evolve according to thermodynamic principles. Energy flows through stars, galaxies, and interstellar gas following predictable patterns. Stars produce energy through fusion, converting lighter elements into heavier ones, while releasing radiation. The balance between gravity and pressure determines how stars evolve over time. These processes occur uniformly throughout the observable universe, as evidenced by the similarities in stellar evolution observed across different regions. Thermodynamic behavior also governs how gas cools and condenses to form new stars within galaxies. The consistency of these processes reinforces the idea that physical laws remain the same wherever they are measured. The geometry of space influences how matter and radiation move. Observations indicate that space on large scales behaves according to models that describe curvature, expansion, and gravitational influence. The distribution of galaxies and the behavior of light traveling across space support the view that the observable universe follows predictable geometric rules. These rules govern how massive objects bend the path of light, producing gravitational lensing effects measurable across the observable domain. The consistency of these effects provides further evidence of the stability of physical laws. Quantum mechanics governs behavior at the smallest scales, defining how particles move, interact, and exist within fields. Although quantum effects become most noticeable in subatomic environments, they also influence large-scale phenomena such as the formation of early cosmic structures. Quantum fluctuations present in the early universe helped seed the density variations that gravity later amplified into clusters and filaments. The distribution of these variations matches predictions from quantum models, suggesting that quantum laws apply uniformly across the observable domain. These laws describe probabilities rather than precise outcomes, yet they remain consistent across measurements. The uniform operation of physical laws across space and time allows scientists to create models that describe both past and future cosmic evolution. These models rely on the assumption that physics remains unchanged across billions of years. Observations support this assumption as structures from the early universe exhibit behavior that matches predictions based on current physical laws. The ability to apply the same models to distant galaxies and to nearby systems strengthens confidence that fundamental physics applies everywhere within the observable universe. Understanding these laws forms the basis for exploring deeper theoretical ideas. By examining how physics operates across the observable domain, scientists can identify which aspects remain well supported by evidence and which remain uncertain. These uncertainties provide opportunities for theoretical frameworks that extend beyond direct observation, but they must remain grounded in known physics. With this layer of physical laws described, the exploration moves inward to the early cosmic conditions that provided the initial environment from which all observable structures formed. The early cosmic environment forms the next inward layer of understanding a region defined not by spatial position, but by the conditions that shape the emergence of structure within the observable universe. These conditions arose when matter, radiation, and space existed in a simpler and more uniform state. As the universe expanded and cooled, these components underwent transitions that allowed particles to form light to travel freely and matter to begin collecting under gravity. Scientific models describe this early period through well-established physics, supported by observations of relic radiation and large-scale structure. Although many details remain under study, the general framework provides a coherent description of how the universe evolved from a state of high temperature and density into the environment where galaxies and clusters now exist. In the earliest measurable moments, temperatures remain high enough that particles and radiation interact constantly. Matter exists primarily as a mixture of rapidly moving particles, and radiation carries energy across extremely short distances before interacting again. As the universe expands, temperatures decline steadily, allowing particles to move more freely. Protons and neutrons combine to form the simplest atomic nuclei through processes governed by nuclear forces. These processes depend on temperature and density, and the predicted distribution of these early elements matches the abundances measured in the observable universe today. This agreement indicates that the early conditions described by physical models accurately represent the environment from which the universe emerged. During this early period, the universe remains filled with radiation that interacts continuously with charged particles. Because of these interactions, light cannot travel far without being scattered. This scattering produces a dense and opaque environment in which matter and radiation behave as a coupled fluid. As the universe continues to expand and cool, conditions eventually change enough to allow electrons to bind to nuclei-forming neutral atoms. Once these atoms form, radiation no longer scatters so frequently and can travel long distances through space. This transition permits light to decouple from matter, creating the earliest detectable radiation that now fills the observable universe. Measurements of this relic light reveal small variations in temperature that correspond to the earliest density fluctuations. These fluctuations later grow under gravity to form the large-scale structures observed today. The formation of early atomic structures marks an important point in cosmic evolution, because it allows matter to begin moving under gravity more freely. Gravity acts on the slight variations in density present in the early universe, amplifying them over time. Regions of slightly higher density attract more matter, while regions of lower density lose matter to their surroundings. These processes occur gradually but become significant as the universe expands. The growth of these fluctuations eventually leads to the formation of galaxies, clusters, and filaments. The patterns observed in relic radiation reflect the initial conditions that guide this process, providing evidence for the physical models describing early evolution. The early environment also includes rapid expansion during a brief period known as inflation, described by scientific models that explain several observed features of the universe. Inflation smooths out irregularities, creates uniform conditions across large regions, and generates quantum fluctuations that later grow into cosmic structures. Although details of this process remain uncertain, the general framework aligns with measurements of relic radiation and large-scale structure. This alignment suggests that expansion during the earliest measurable moments plays an important role in shaping the universe as observed today. Within the context of this narrative, inflation serves as a description of how early conditions evolve without implying anything about regions beyond observation. After the formation of the earliest atoms, matter in the universe exists primarily as hydrogen and helium gas. Over time, this gas begins to collect under gravity, forming dense regions that collapse into the first stars. These early stars become sources of light that begin to illuminate the previously dark universe. Their formation marks a transition from a uniform gas-filled environment to one where luminous structures emerge. The radiation produced by these early stars interacts with gas, heating it and altering its state. This process gradually ionizes much of the hydrogen in the universe, allowing radiation to travel more freely and shaping the large-scale environment in which galaxies later form. As stars form and evolve, they produce heavier elements through fusion. When these stars reach the end of their life cycles, they expel these elements into space, enriching the surrounding gas. This enriched gas forms new generations of stars and contributes to the formation of planets and other structures. Although this process occurs long after the earliest cosmic conditions, it originates from the physical laws governing the early universe. The distribution of elements observed in galaxies today reflects the history of star formation and the nuclear processes that began during the earliest eras. The early universe contains regions where conditions remain exceptionally dense. Over time, these dense regions may collapse under gravity to form supermassive black holes located at the centers of many galaxies. Models of early cosmic evolution predict the environments in which such objects may form. Observations of distant galaxies reveal black holes that appear to have grown rapidly during the early stages of cosmic history. These findings support the view that gravitational collapse began early and contributed to the formation of large-scale structures. Although the specific processes that lead to black hole formation remain under study, the general framework aligns with known physics and observational evidence. Throughout these early stages, the expansion of the universe continues to shape the evolution of matter and radiation. As space expands, the distances between regions increase and the density of matter decreases. This expansion slows the growth of structure but does not halt it. Gravity continues to pull matter into denser regions, forming the framework of clusters and filaments. The rate of expansion influences how quickly structures form and how matter moves within them. Measurements of the expansion rate across different epochs allow scientists to test physical models and refine their understanding of cosmic evolution. The early universe becomes less uniform as time progresses. Small variations in density grow into the first cosmic structures, creating the seeds for galaxies and clusters. Although the universe remains much simpler than it is today, the patterns established during these early stages determine the arrangement of matter throughout the observable domain. The behavior of radiation. the formation of atoms, and the influence of gravity all contribute to these early patterns. By studying the relic radiation, scientists can trace these patterns back to their origins and understand how the universe evolved from a uniform state into one filled with complex structures. With the early cosmic conditions explored, the next inward layer examines the limits of observation. These limits arise from the finite speed of light, the expansion of space, and the time available for signals to reach the present. Understanding these boundaries helps clarify how far scientific knowledge can extend within the observable universe before transitioning to theoretical frameworks that describe what may lie beyond direct measurement. The observable universe, though vast, remains limited by the distance that light has been able to travel since the earliest detectable moments. These limits arise naturally from the finite speed of light, the expansion of space, and the amount of time radiation has had to reach the present. Because of these constraints, the universe visible today represents only a portion of the full cosmic expanse. These observational boundaries do not indicate an edge or a physical barrier. Instead, they reflect the maximum range from which information has arrived. Understanding this boundary forms a crucial layer in the exploration of cosmic structure because it defines where measurable knowledge ends and where theoretical models begin. The most fundamental limit comes from the finite speed at which light travels. Light moves extremely quickly, yet it still requires time to cross cosmic distances. Because the universe has a finite age measured in billions of years, light from regions beyond a certain distance has not had enough time to reach Earth. As a result, those regions remain unobservable at present. This limit expands as time passes because additional light continues to arrive from progressively more distant regions. Thus, the observable boundary grows with cosmic time, not through the movement of matter, but through the arrival of new signals. The expansion of space further influences what can be observed. As galaxies recede from one another, the distance between regions increases over time. Some regions recede so rapidly that even light travelling toward Earth becomes stretched and slowed by expansion. In extreme cases, light emitted today may never reach the observable domain because expansion outpaces its progress. These regions lie beyond a horizon formed by the combined effects of light speed and expansion. This horizon represents a limit for future observation, defining a boundary that expands over long intervals, yet still excludes some regions permanently. Although these areas exist within the broader universe, they remain inaccessible to direct measurement. The relic radiation from early cosmic conditions provides a clear example of observational boundaries. This radiation originates from a time when the universe transitioned from opaque to transparent. Because light from earlier times could not travel freely, no information exists from before that period in the form of electromagnetic signals. This establishes a temporal boundary as well as a spatial one. The earliest observable radiation forms a sphere around Earth, representing the most distant surface from which light has arrived. Beyond this surface lie regions that existed during earlier times, but cannot be observed through light-based measurements. Although other forms of information might theoretically carry signals from these earlier epochs, none have been detected. In addition to spatial and temporal limits, observational boundaries arise from the sensitivity of instruments. Telescopes detect light across many wavelengths, but some objects remain too faint or too distant to measure with current technology. Radiation from extremely far regions becomes stretched to wavelengths that may fall beyond detection. Gas clouds or dust may obscure light from certain regions, preventing signals from reaching instruments even when they are within observable range. These technological and environmental limits do not represent fundamental constraints, but they influence practical measurement capabilities. Over time, improvements in instrumentation expand the range of detectable objects and wavelengths, allowing scientists to refine their understanding of the observable domain. Gravitational waves provide an alternative form of information that travels through the universe. These waves result from the motion of massive objects, and their detection requires highly sensitive instruments. Although gravitational wave observatories have detected events from distant regions, the number of detectable signals remains limited by technological capabilities. Because gravitational waves travel without interacting significantly with matter, they can carry information from environments that light cannot penetrate. Their use expands the observational domain, yet they remain bounded by instrument sensitivity and the number of detectable events. Thus, they provide valuable but still limited insight into the broader universe. Neutrinos also travel across vast distances with little interaction. These particles originate from processes such as nuclear reactions in stars or explosive astrophysical events. They carry information about these environments, but they remain extremely difficult to detect. As a result, the neutrino-based observational domain remains narrow compared to electromagnetic observations. Nevertheless, neutrinos represent another means of probing the universe within the limits set by physical properties and instrument capabilities. Observation depends not only on the arrival of signals, but also on the interpretation of data. Light traveling across expanding space becomes stretched, altering its wavelength and energy. Scientists must account for these changes to determine distances, velocities, and physical conditions. Although models accurately describe how expansion affects light, the interpretation of extremely distant signals becomes more uncertain, because minor errors in measurement can lead to significant differences in inferred properties. This uncertainty reflects the challenge of observing regions near the limits of detectability rather than any lack of understanding in the physical laws themselves. The observable universe also contains regions where information travels in forms other than light or particles. Gravitational interaction provides indirect information about mass distribution even in regions where light may not be visible. For example, the presence of dark matter becomes evident when observing the motion of galaxies or the bending of light around massive structures. These indirect observations help extend knowledge beyond what direct signals reveal. However, they remain constrained by the need for visible or detectable interactions with matter that can be measured. Limits of observation define the boundary between measurable science and theoretical extension. By identifying the maximum range of detectable signals, scientists can build models that describe the universe within the observable domain, and use these models to explore theoretical scenarios that extend beyond direct measurement. These theories rely on the assumption that physical laws remain consistent across the unobserved regions. While such assumptions cannot be confirmed directly, they allow models to remain grounded in the physical behavior observed across the accessible universe. Recognizing observational boundaries prepares the exploration to move inward to the mathematical structures used to describe these accessible regions. These structures form the basis for linking physical laws with cosmic evolution and provide the foundation for theoretical models that later describe broader possibilities. The mathematical framework of cosmology forms the next inward layer, describing the observable universe through equations that link matter, radiation, space, and time. This framework does not extend into speculation about unobserved realms. Instead, it provides the structure needed to understand how known physical laws shape measurable cosmic behavior. These mathematical descriptions allow scientists to model expansion, predict how galaxies move, estimate the growth of structure, and interpret the signals that reach Earth. Although mathematics operates as an abstract language, Its purpose within this context remains grounded entirely in describing the universe seen through observation. Central to this framework is the mathematical description of how space expands. Models describe space as a dynamic entity that stretches over time, influencing the distance between galaxies even when those galaxies remain gravitationally bound within clusters or filaments. This expansion is represented through equations that relate the scale of space to cosmic time. These equations define how the distance between two non-interacting galaxies increases as time progresses. Observations of distant galaxies support this description, showing that their light stretches to longer wavelengths as it travels through expanding space. The relationship between distance and redshift fits the predictions of these mathematical models, providing a consistent representation of cosmic behavior. Gravity appears in this framework through equations that relate matter density, pressure, and energy to the curvature of space. These equations predict how matter moves within the universe, how structure forms, and how radiation travels across large distances. In regions where matter density increases, curvature also increases, causing objects to follow paths that reflect the influence of gravity. This mathematical relationship explains why galaxies gather into clusters and why light bends as it passes near massive structures. Observations of gravitational lensing match these predictions, confirming that the mathematical description accurately reflects how matter and radiation interact across the observable domain. The framework also describes how small fluctuations in early matter density grow into large-scale structures. Models represent these fluctuations as variations in density that evolve under gravity. Equations predict how quickly these fluctuations grow and how they combine into the cosmic web observed today. These predictions match the distribution of galaxies, clusters, and voids across the observable universe. The agreement between models and observations strengthens confidence in the mathematical representation of early evolution. Because these models rely on known physical laws, they remain grounded in measurable science, even when describing conditions that existed long before galaxies formed. Radiation plays an important role in this mathematical framework. Its behavior is governed by equations that describe how energy moves through expanding space. As the universe expands, the energy of radiation decreases, causing wavelengths to stretch. This effect, known as redshift, forms a critical tool for measuring distance and interpreting cosmic history. Mathematical models describe how radiation cools as space expands, predicting the temperature of relic radiation that fills the universe today. Measurements of this radiation match these predictions, demonstrating that the mathematical framework accurately reflects physical behavior. Quantum mechanics contributes another layer of mathematical structure. At extremely small scales, the behavior of particles and fields becomes uncertain, governed by probabilities rather than fixed outcomes. Mathematical models describe this uncertainty through equations that predict the likelihood of different particle states. In the early universe, tiny quantum fluctuations influenced the distribution of energy and matter. These fluctuations, when amplified by cosmic expansion, seeded the density variations observed in relic radiation. The mathematical connection between quantum fluctuations and large-scale structure offers a link between the smallest scales and the largest observable patterns. This connection remains grounded in known physics and does not imply anything beyond the observable universe. The framework also defines how matter, radiation, and space interact through conservation laws. These laws describe how energy remains balanced within the universe, how matter density changes as space expands, and how radiation shifts across wavelengths. Conservation laws ensure that models remain internally consistent. For example, as space expands, the energy density of matter decreases, because the same amount of matter occupies a larger volume. Radiation energy density decreases even more quickly due to wavelength stretching. These behaviors match observations across many scales, demonstrating that the mathematical framework accurately tracks how matter and radiation evolve. The use of mathematical symmetry simplifies many aspects of cosmic modeling. Symmetry describes conditions where physical behavior remains the same across large regions. For example, on sufficiently large scales, the universe appears uniform in all directions. This uniformity allows models to treat space as having consistent properties across vast distances. Although structures such as clusters and filaments introduce local variations, the large-scale symmetry simplifies calculations of expansion and matter distribution. This symmetry-based modeling does not imply homogeneity beyond the observable universe. It simply reflects the measured pattern within the accessible region. Probability enters the mathematical framework when describing how certain processes unfold. For example, the distribution of galaxies follows predictable statistical patterns. These patterns arise from random fluctuations in the early universe that gravity later amplified. Models use probability to describe how these fluctuations combine to create the structures observed today. The statistical nature of these models reflects the inherent uncertainty of quantum fluctuations, yet the overall patterns remain highly predictable. Because probability-based predictions match observations, the mathematical framework remains firmly rooted in empirical evidence. Within this mathematical structure, uncertainties still exist. Some equations describe behavior accurately, but rely on parameters whose values are not known with perfect precision. These parameters include the total amount of matter in the universe, the rate of expansion at different times, and the distribution of dark matter. Although measurements continue to refine these values, small uncertainties remain. These uncertainties do not undermine the overall framework. Instead, they define areas where further observation improves understanding. Recognizing these limits helps distinguish well-established aspects of the framework from those that still require refinement. The mathematical description of the observable universe remains one of the most powerful tools in cosmology. It allows scientists to describe the past, interpret the present, and predict future behavior without extending beyond known physics. It does not assign meaning or purpose to cosmic evolution, but simply describes the behavior of matter, radiation, and space through consistent rules. With this mathematical layer complete, the exploration now turns inward to the smallest scales, where quantum behavior governs the motion of particles and fields. This shift moves from cosmic equations to the domain of quantum processes that influence physical behavior at the smallest measurable levels. At the smallest measurable scales, the universe behaves according to quantum principles that describe particles and fields through probabilities rather than fixed trajectories. This quantum domain forms the next inward layer, where matter and energy no longer follow continuous paths, but instead exhibit discrete behaviors governed by uncertainty, wave-like properties, and interactions that unfold at extremely small distances. Although these processes occur far below the scale of galaxies or atoms, they influence the evolution of the observable universe by shaping how particles form, how forces operate, and how early fluctuations arise. This layer focuses on the quantum behavior that underlies all larger structures without extending beyond known physical laws or implying phenomena outside the observable region. In the quantum domain, particles exist as excitations of fields that permeate space. Each type of particle corresponds to a specific field, and interactions occur when fields influence one another. This framework describes particles not as tiny solid objects, but as localized disturbances within underlying structures. The behavior of these disturbances follows mathematical rules that predict the probability of finding a particle in a particular state. Because these probabilities govern outcomes rather than fixed paths, quantum mechanics introduces uncertainty into even the simplest interactions. This uncertainty does not reflect limits in measurement, but represents a fundamental property of nature at small scales. One of the defining features of quantum behavior is wave-particle duality, the property that particles such as electrons and photons behave both as particles and as waves depending on the conditions of observation. These wave-like characteristics allow particles to interfere with themselves, produce patterns that depend on the shape of experimental setups, and occupy states that cannot be described through classical trajectories. Although such behavior seems far removed from large-scale cosmic structure, it underlies processes such as atomic formation, radiation, emission, and energy transfer. These processes shape the evolution of stars, galaxies, and the early universe. Quantum fields also give rise to fluctuations, temporary changes in field values that occur even in empty space. These fluctuations arise because the energy of a field cannot remain fixed with perfect stability. Instead, fields experience momentary changes that create pairs of particles and antiparticles before returning to their original state. In the early universe, these fluctuations influence the distribution of matter and energy. Expansion amplified small variations, creating the initial patterns that gravity later turned into the large-scale structures observed today. The properties of these fluctuations help explain the statistical patterns present in relic radiation, supporting the connection between quantum processes and cosmic evolution. At the atomic cell, quantum behavior determines how electrons arrange themselves around nuclei. Electrons occupy specific energy levels rather than moving along defined orbits. These levels result from the wave-like nature of electrons and the mathematical rules governing allowed states. Transitions between levels produce or absorb radiation at specific wavelengths. This radiation forms the basis for understanding the composition of stars and galaxies. Because quantum rules determine the structure and behavior of atoms, they also determine the properties of matter throughout the observable universe. Quantum processes also govern nuclear interactions. The strong nuclear force binds protons and neutrons within atomic nuclei, and this force operates at distances far smaller than atoms. The weak nuclear force influences processes that change one type of particle into another, playing an essential role in nuclear reactions within stars and the formation of early elements. These interactions follow mathematical rules consistent across all observed environments. The distribution of elements in galaxies reflects the influence of quantum processes acting over billions of years. Particles also exhibit entanglement, a property in which two or more particles become correlated in ways that cannot be explained through classical communication. When entangled particles are created, their states remain linked even when separated by large distances. Changes in the state of one particle correspond to predictable changes in the other. This behavior does not violate physical limits, such as the speed of light, because it does not transmit information. Instead, entanglement reflects the underlying structure of quantum states. Although entanglement plays little role in large-scale cosmic structure, it forms an essential part of the mathematical description of particles and fields. Quantum mechanics introduces probabilities into every measurement. Instead of predicting a single outcome, it predicts the likelihood of each possible outcome. These probabilities follow consistent rules described by mathematical structures known as wave functions. When a measurement occurs, the system enters a definite state, but before measurement, the system exists in a combination of possible states. This probabilistic nature influences how early fluctuations form and how particles behave in high-energy environments. Because the early universe contained high-energy fields and rapidly changing conditions, quantum mechanics played an important role in shaping its evolution. The interaction between quantum processes and the expansion of space influences the distribution of matter across the observable universe. As space expands, quantum fluctuations stretch to larger scales. These stretched fluctuations become the seeds of later structure. Without this amplification, the universe would remain nearly uniform, and galaxies could not form. The distribution of these early fluctuations matches predictions from quantum models, confirming that quantum mechanics describes the behavior of the early universe accurately. Quantum behavior also influences the properties of dark matter and other components of the universe. Although dark matter has not been directly observed through electromagnetic interactions, its gravitational influence supports models in which it behaves as a particle or field governed by quantum rules. These models remain grounded in known physics and do not extend beyond the observable universe. They simply describe possible quantum properties consistent with observed gravitational behavior. Despite the success of quantum mechanics, some aspects remain uncertain. The nature of quantum fields at extremely high energies, the full behavior of particles during the earliest measurable moments, and the relationship between quantum mechanics and gravity remain areas of active research. These uncertainties do not undermine the framework, but indicate where further refinement may occur. They also highlight the boundary between well-tested physical laws and theoretical extensions. By examining the quantum domain, scientists connect the smallest scales to the largest structures. Quantum mechanics shapes the formation of atoms, the behavior of light, the growth of early fluctuations, and the evolution of stars. It operates consistently throughout the observable universe, demonstrating that even the most complex cosmic patterns emerge from processes that originate at extremely small scales. With the quantum foundation described, the progression now moves inward to the bridge between quantum fluctuations and cosmic structure, where early variations influenced by quantum behavior expand to form the seeds of galaxies, clusters, and filaments. The bridge between quantum behavior and cosmic structure forms the next inward layer, where the smallest fluctuations in energy and density begin to influence the evolution of the universe on scales far larger than atoms. This layer focuses on how quantum variations present during the earliest measurable moments become stretched by expansion, creating patterns that gravity later transforms into the large-scale structures observed today. These fluctuations do not represent randomness without constraint. Instead, they follow statistical properties determined by quantum mechanics and by the physical conditions present when the universe was extremely young. As the universe expands, these early variations move from microscopic scales to macroscopic scales, where they play a defining role in shaping matter distribution across the observable domain. During the earliest era relevant to observation, the universe exists in a state where rapid expansion influences the behavior of quantum fields. Small variations appear naturally within these fields because quantum mechanics prevents absolute uniformity. These variations occur as momentary differences in energy or density across very small distances. As expansion proceeds, distances between regions increase, stretching these variations across space. What begins as a fluctuation at a microscopic scale becomes a measurable difference at much larger scales. These differences persist because they become imprinted on the distribution of matter and radiation, providing the initial seeds for later growth under gravity. The pattern of these fluctuations follows statistical rules predicted by quantum theory. These rules describe how variations should appear across different scales, with certain sizes of fluctuations being more common than others. Measurements of relic radiation reveal temperature variations that match these predicted patterns. These variations correspond to differences in density at the time when radiation decoupled from matter. The close agreement between predictions and observations indicates that the connection between quantum fluctuations and cosmic structure forms a consistent and measurable process. This connection allows scientists to trace the evolution of the universe from extremely small scales to the complex structures observed today. As expansion continues, regions with slightly higher density begin to interact with gravity more strongly. Gravity pulls matter toward these regions, enhancing the differences created by the initial fluctuations. Regions with slightly lower density experience reduced gravitational attraction, becoming less likely to accumulate matter. Over long intervals, gravity amplifies these early differences, gradually increasing the contrast between denser and less dense regions. The early patterns imprinted by quantum fluctuations thus form the foundation for the cosmic web, influencing the locations of future clusters, filaments, and voids. Relic radiation provides a detailed map of these early patterns. Its temperature variations correspond to density differences at the time when the universe became transparent to radiation. Hotter regions represent areas of slightly higher density, while colder regions represent areas of slightly lower density. These temperature variations remain extremely small, yet they mark the earliest evidence of structure formation. When scientists compare these variations with predictions from quantum models, they find close agreement across many scales. This agreement strengthens the link between quantum fluctuations and large-scale structure. The growth of these fluctuations depends on the interplay between gravity and pressure. In regions with higher density, gravity pulls matter inward. However, radiation pressure resists compression in the early universe. The balance between these forces determines how quickly fluctuations grow. Once radiation ceases to dominate the energy density, gravity becomes the primary influence, allowing fluctuations to grow more rapidly. This transition marks an important stage in cosmic evolution because it allows matter to collect more freely, laying the groundwork for the eventual formation of galaxies. Dark matter plays a central role in this process because it interacts through gravity, but not through radiation. During early stages, when radiation still interacts strongly with ordinary matter, dark matter begins to collapse into denser regions more quickly. This collapse forms a gravitational framework that later guides the motion of ordinary matter. As ordinary matter cools and decouples from radiation, it falls into the potential wells created by dark matter. These wells trace the shapes of the early fluctuations, ensuring that galaxies and clusters form in regions where quantum variations originally created slightly higher densities. This relationship provides a clear example of how microscopic processes influence cosmic scale behavior. As fluctuations grow, they begin to form the first structures capable of collapsing under gravity. These structures remain small compared to galaxies, but they provide the environment in which gas begins to collect. The collapse of gas into these regions forms the earliest stars, which then alter their surroundings through radiation and chemical enrichment. Although these early stars form long after the initial fluctuations, the distribution of star-forming regions reflects the patterns established by those fluctuations. The structure of galaxies that appear later also reflects these early patterns, demonstrating the continuity between quantum behavior and observable structure. Mathematical models describe how fluctuations of different sizes grow at different rates. Larger fluctuations grow slowly because their gravity is spread over greater distances. Smaller fluctuations grow more quickly but may be suppressed if radiation pressure remains strong. These models predict a specific pattern known as the power spectrum, which describes how variation strength changes with scale. Measurements of relic radiation reveal a power spectrum that matches these predictions, offering further evidence that the mathematical connection between quantum behavior and cosmic structure accurately describes early evolution. Although the connection between quantum fluctuations and cosmic structure remains well supported, some aspects remain uncertain. The exact nature of the fields responsible for generating fluctuations, the conditions present during the earliest measurable moments, and the precise sequence of events during rapid expansion remain under active investigation. These questions do not undermine the overall framework, but highlight the boundary between well-tested physics and areas where deeper understanding continues to develop. The observable universe provides enough information to reconstruct many aspects of early evolution, but details from beyond the observable boundary remain inaccessible. The bridge between quantum and cosmic scales demonstrates how the smallest processes influence the largest structures. Tiny variations in early fields governed by probabilities and uncertainties evolve into the patterns that guide the distribution of galaxies across billions of light years. This continuity does not require speculation beyond known physics. Instead, it reflects the natural progression from microscopic behavior to macroscopic structure. With this bridge described, the exploration moves inward into the era of rapid expansion that shapes these early patterns further and influences the distribution of matter throughout the observable universe. The era of rapid expansion known as inflation forms the next inward layer, marking a stage in cosmic history during which the universe undergoes extremely fast growth over a very short interval. This expansion smooths irregularities, stretches quantum fluctuations to scales that later seed structure formation, and establishes many of the properties measured in relic radiation. Although details of inflation remain under study, the general framework appears consistent with observations and aligns with mathematical models describing the early universe. Within this narrative, inflation serves as the process that transforms microscopic variations into the initial patterns guiding the growth of structure throughout the observable domain. During inflation, the universe expands at an accelerating rate, increasing distances between regions faster than they can interact. This rapid expansion makes the universe appear uniform on large scales, because it stretches out any initial irregularities. Regions that might have varied significantly before inflation become nearly identical after expansion spreads them across vast distances. This smoothing effect explains why the observable universe appears so uniform in temperature and structure. Without such a mechanism, it becomes difficult to reconcile the uniformity of relic radiation with the idea that distant regions could not have exchanged information through light or other signals before expansion slowed. Despite the smoothing effects of inflation, quantum fluctuations persist at microscopic scales. As expansion stretches these fluctuations, they become imprinted on the fabric of space. Fluctuations that begin as extremely small differences in energy or density grow to cosmic scales as inflation pushes them outward. Once inflation ends, these fluctuations remain frozen into the distribution of matter and radiation. Later, when ordinary expansion continues and gravity begins to dominate structure formation, these early differences guide the flow of matter into the patterns that eventually form galaxies and clusters. Mathematical models describing inflation predict specific patterns in the distribution of fluctuations. These patterns appear as statistical variations in relic radiation, which reveal the strength of fluctuations across different scales. The smoothness of the large-scale universe, combined with the small irregularities measured in relic radiation, provides strong evidence for the influence of inflation. The correlation between predictions and observations suggests that inflation accurately describes a critical stage in early evolution. Inflation also influences the geometry of the observable universe. By stretching space over enormous scales, inflation drives the universe toward flatness, meaning that parallel lines remain parallel over large distances. Measurements of relic radiation support this prediction by indicating that the observable universe behaves very close to flat. Although small deviations may exist, the overall geometry matches the expectations of inflationary models. This consistency offers further support for the idea that rapid expansion shapes the universe during its earliest measurable moments. During inflation, energy stored in the field associated with expansion drives the rapid growth of space. As inflation ends, this energy converts into particles and radiation, heating the universe and initiating the next stage of cosmic evolution. This process, known as reheating, creates the environment in which the earliest atomic nuclei begin to form. Although scientists continue to study the exact mechanisms of reheating, the overall sequence forms an important part of the theoretical framework describing early conditions. Inflation also influences the distribution of gravitational waves across the observable universe. As space expands rapidly, quantum fluctuations in gravitational fields stretch to large scales. These fluctuations may produce gravitational waves detectable through their influence on relic radiation. Scientists search for specific patterns in relic radiation that would indicate the presence of such waves. Although these patterns have not yet been confirmed, their detection would provide further support for inflationary models. The absence of confirmation at present reflects observational limitations rather than contradictions in the theoretical framework. One of the notable features of inflation is its ability to explain why the observable universe appears homogeneous on large scales while still containing small variations necessary for structure formation. The smoothing effect ensures uniformity, while the stretching of quantum fluctuations introduces the irregularities needed to form galaxies and clusters. This balance emerges naturally from the mathematical description of inflation, demonstrating how a single physical process can address multiple aspects of cosmic evolution. Although inflation remains a widely accepted model, uncertainties remain regarding the exact nature of the field driving expansion. Scientists propose various models with different properties for this field, but all share the feature of rapid expansion, followed by reheating. Differences between models influence the predicted patterns of fluctuations. Observations continue to refine these predictions, helping narrow down possible models. This ongoing refinement demonstrates how theoretical frameworks evolve in response to new measurements. Inflation sets the stage for the growth of structure by establishing the initial condition from which gravity later forms the cosmic web. Once inflation ends, the universe continues to expand more slowly, allowing matter and radiation to interact according to known physical laws. Gravity begins to amplify the fluctuations created during the inflation, guiding matter toward denser regions. Over long intervals, these regions form clusters, filaments, and voids. Without inflation, the initial patterns would differ significantly, leading to a universe with a different distribution of structure. By stretching space and imprinting patterns on the distribution of matter and radiation, inflation links the quantum domain to the large-scale universe. It transforms microscopic fluctuations into macroscopic structures while preserving uniformity across enormous distances. This connection provides a coherent framework for understanding how the universe evolves from its earliest measurable moments to the structured environment observed today. With inflation described, the exploration moves inward to theoretical multiverse models that arise from some interpretations of cosmic expansion while remaining grounded in scientific descriptions that do not assert the existence of unobservable realms. The next inward layer enters the domain of theoretical multiverse models, which arise from scientific attempts to understand the implications of early cosmic expansion quantum behavior and mathematical cosmology. These models do not assert the existence of unobservable realms, but describe possibilities that emerge naturally when extending known physics into regimes that cannot yet be tested directly. They exist within the framework of scientific theory, using established principles to explore what may occur under certain conditions. Although these models provide structured ways of thinking about cosmic evolution, they remain speculative until supported by observational evidence. Within this narrative, they appear only as theoretical constructs consistent with scientific practice. One category of multiverse models emerges from the inflationary framework. In some interpretations, inflation does not end uniformly across all regions of space. Instead, certain regions may stop inflating while others continue. Each region where inflation ends becomes a distinct space-time domain with its own distribution of matter and radiation. These domains expand so rapidly that they become effectively isolated from one another. Although this framework arises naturally from some versions of inflation, it remains theoretical because no direct observation can detect regions beyond the observable universe. Within this narrative, such models represent an extension of the inflationary process, without implying physical access to these regions. Another category arises from quantum mechanics, specifically from mathematical descriptions that treat all possible outcomes of a quantum event as part of a broader structure. In these models, each outcome evolves independently once a measurement occurs, forming separate branches of a mathematical structure that describes the quantum state. These branches do not interact or exchange information. Because they arise from the mathematics of quantum theory, they represent a different kind of theoretical multiverse that does not depend on cosmic expansion. This interpretation remains a mathematical construct rather than a physical claim about the existence of separate universes. Still another theoretical category arises from mathematical cosmology, where the equations describing spacetime allow solutions with different physical constants or geometric properties. These solutions exist as possibilities within the mathematical framework, but do not imply physical reality unless supported by evidence. Scientists use these models to explore how different values of physical constants would influence the evolution of matter and radiation. These exercises help clarify why certain constants play essential roles in cosmic evolution, but they do not assert that regions with different constants exist. Instead, they serve as tools for understanding how physical laws operate within the observable universe. Theoretical multiverse models also arise from attempts to unify gravity with quantum mechanics. Some frameworks describing quantum gravity suggest that spacetime may have multiple stable configurations, each corresponding to different physical conditions. These configurations appear in mathematical solutions without implying physical existence. Their purpose is to explore how fundamental interactions might behave at extremely high energies. Scientists continue to investigate these models to determine whether they produce predictions testable within the observable universe. Until such predictions arise, these models remain speculative yet scientifically structured. Despite their differences, all theoretical multiverse models share a common origin in established physics. They extend known principles to explore consequences that cannot be observed directly. These extensions follow scientific reasoning but do not replace empirical evidence. They remain provisional, subject to revision, as new measurements refine understanding. Because direct observation of regions beyond the observable universe remains impossible, these models cannot be confirmed through current instruments. Instead, they provide a framework for exploring possible implications of physical laws. The existence of multiverse models does not imply fragmentation or duplication of the observable universe. Instead, these models describe how variations may arise under certain theoretical conditions. For example, in inflation-based models, separate regions form when inflation ends at different times. In quantum models, separate branches form when quantum events evolve into distinct mathematical outcomes. In mathematical cosmology, separate solutions represent alternative configurations of physical constants. Each model treats these possibilities differently, yet all remain theoretical until evidence appears within the observable domain. Scientific practice treats these models cautiously. They provide tools for exploring the boundaries of known physics, but they must remain consistent with all established observations. A theoretical model becomes scientifically useful only when it generates predictions testable through data. Some multiverse models attempt to identify such predictions. For example, inflation-based models may influence the pattern of fluctuations in relic radiation. Quantum-based models may provide insights into decoherence and the behavior of entangled systems. Mathematical models may refine understanding of how physical constants influence cosmic evolution. These connections allow multiverse theories to contribute to scientific inquiry without asserting untested claims. Uncertainty remains an essential part of these models. Scientists recognize the limitations of observation and the role of theory in exploring unknown regimes. Multiverse models represent one way to investigate those regimes using structured reasoning. They do not aim to replace empirical observation but to complement it. By exploring theoretical possibilities, scientists can identify which aspects of fundamental physics require further investigation. As new data arrive, models evolve to reflect improved understanding. Because multiverse models exist at the boundary of observation and theory, they illustrate how scientific inquiry progresses. First, empirical evidence establishes a foundation. Next, theoretical frameworks extend that foundation into regimes not yet accessible. Finally, observations refine or dismiss these frameworks. This process ensures that even speculative models remain grounded in known physics. Multiverse theories occupy this space, offering structured possibilities without implying conclusions. Within this narrative, multiverse models appear only as theoretical constructs used to explore consequences of inflation, quantum behavior, or mathematical solutions. They do not introduce speculative description or cosmological meaning. Instead, they represent a structured and scientifically neutral extension of established laws. Their inclusion marks a transition from observable cosmic behavior to theoretical possibilities grounded in scientific reasoning. With these models described, the exploration proceeds inward to the next layer, which examines how such theoretical domains could differ from the observable universe in physical conditions, while remaining entirely hypothetical within scientific practice. The inward progression now enters the layer of independent cosmic regions as described in theoretical multiverse models, focusing strictly on how such regions are defined within scientific frameworks, rather than asserting their existence. These regions arise in models where early expansion quantum processes or mathematical solutions produce separate space-time domains that evolve without interaction. Within this narrative, these domains remain hypothetical constructs used to examine how known physical laws might operate under different initial conditions. Their inclusion serves only to clarify how scientific theory organizes possibilities beyond the observable universe, while maintaining strict neutrality regarding their reality. In inflation-based models, independent regions form when rapid expansion ends at different times across vast areas of space. Where inflation stops matter, and radiation can begin to evolve, forming environments similar in structure to the early observable universe. In areas where inflation continues, expansion accelerates, further pushing these domains beyond communication with one another. Each region becomes isolated due to distances expanding faster than signals can travel. Although these domains share a common origin in the inflationary process, they follow independent evolutionary paths determined by local conditions. These conditions may include small variations in density, temperature, or field values that remain after inflation slows. Because these regions cannot exchange information, scientists treat them as independent elements of theoretical models rather than as components of an observable framework. Quantum-based multiverse interpretations describe independence differently. They treat distinct outcomes of quantum events as separate branches of a mathematical structure. Each branch evolves according to the same physical laws, but represents a different realization of possible states. These branches do not interact and cannot influence one another, making them independent within the mathematical framework. Their independence arises not from spatial separation, but from the structure of quantum states. Although this model provides a consistent way to describe quantum probabilities, it remains mathematical rather than physical, unless supported by observational evidence. Mathematical cosmology offers another perspective, presenting independent cosmic regions as distinct solutions to the equations describing spacetime. These solutions represent possible configurations that differ in initial conditions, curvature, or physical constants. Each solution forms a separate domain within the mathematical framework, evolving according to its specific parameters. These regions do not interact because they correspond to different solutions of the governing equations. Scientists use these models to explore how variations in physical conditions influence cosmic evolution. Although these solutions provide valuable insight, they remain theoretical and do not indicate that such regions exist beyond the observable universe. Within these theoretical frameworks, independent cosmic regions serve as tools for understanding how physical laws depend on initial conditions. For example, in models where inflation produces separate regions, each domain may inherit slightly different values of fields governing early expansion. These differences could influence local behavior of matter radiation and structure formation. In quantum-based models, each branch reflects a different outcome of a quantum event, showing how systems evolve under varied conditions while remaining consistent with the same underlying laws. In mathematical models, changes in constant values or geometric properties alter how matter clusters or how radiation behaves, demonstrating the sensitivity of cosmic evolution to foundational parameters. Despite their differences, all independent region models maintain consistency with known physics within each domain. Physical laws remain unchanged even if initial conditions vary. This consistency ensures that theoretical regions do not introduce contradictions into established scientific frameworks. The independence of these regions reflects an absence of causal interaction, not a difference in physical laws, unless specifically defined by model constraints. Scientists maintain this distinction to avoid misinterpreting theoretical constructs as physical claims. Independence also implies that information cannot pass between these domains. Inflation-based models prevent communication due to rapid expansion. Quantum models prevent interaction due to the structure of quantum states. Mathematical models prevent mixing because each solution exists within its own representation of space-time. This isolation ensures that theoretical regions do not affect the observable universe. As a result, these models remain speculative without influencing empirical science directly. Their role lies in exploring how physical laws might behave under varied scenarios. The concept of independence raises questions about observability. Because these regions cannot be accessed through signals, they remain beyond empirical reach. This limitation means scientists cannot confirm or refute their existence using current methods. Multiverse models acknowledge this constraint, treating independent regions as hypothetical components rather than as measurable parts of the universe. The distinction between observable and theoretical domains remains essential, ensuring that scientific inquiry stays grounded in evidence. Even within theoretical frameworks, independent regions follow predictable mathematical evolutions. Inflation-based domains expand rapidly, cooling and developing structures similar to those in the observable universe. Quantum-based branches evolve through deterministic equations even though outcomes differ. Mathematical domains follow the rules of their governing equations, producing cosmic evolutions shaped by chosen parameters. Although these evolutions differ across models, they illustrate how variations in early conditions produce diverse outcomes. This variety helps scientists understand the sensitivity of cosmic evolution to its starting points. Independent regions also offer insight into how cosmological models handle uncertainty, when initial conditions remain unknown, or when mathematical frameworks allow multiple solutions in dependent region. Models help scientists explore ranges of possibilities. These explorations clarify which features of the observable universe depend on specific parameters and which appear robust across many conditions. For example, structure formation may occur across a wide range of initial densities, while certain element abundances may depend sensitively on early temperatures. By examining these patterns, scientists gain insight into the flexibility of physical laws. Theoretical independent regions provide a structured way to think about spacetime beyond the observable boundary, without assigning meaning or physical significance. Their purpose lies in clarifying how cosmic evolution responds to variations, rather than suggesting that such regions exist. Because science relies on empirical evidence, these models remain tools rather than conclusions. As observational capabilities improve, some aspects of these frameworks may become testable, others will remain purely theoretical. Within this narrative, these independent regions represent the boundary between models grounded in observation and models extending into hypothetical domains. They help define the scope of scientific possibility while remaining constrained by known physics. With their role clarified, the exploration moves inward to the next layer, where theoretical variations in physical conditions appear within these domains, showing how changes in constants or properties might alter cosmic evolution while remaining entirely hypothetical. The inward path now enters the layer where theoretical variations in physical conditions appear within the independent cosmic regions described by scientific models. These variations do not assert the existence of alternate universes. Instead, they examine how cosmic evolution might differ if physical constants, particle properties, or initial conditions varied within the mathematical frameworks that allow such possibilities. Scientists study these hypothetical variations to understand the sensitivity of cosmic behavior to the laws and parameters measured in the observable universe. By exploring how different values or arrangements influence outcomes, researchers gain insight into why certain features appear stable across a range of conditions while others require precise values. This layer remains strictly theoretical, grounded in scientific modeling rather than empirical observation. One form of variation considered in these models involves differences in physical constants. Constants such as the gravitational constant, the charge of the electron, or the strength of nuclear forces determine how matter behaves at fundamental levels. Mathematical cosmology allows these constants to take different values in hypothetical domains, revealing how cosmic evolution might unfold under altered conditions. For example, if gravity were stronger matter, might collapse into dense structures, more quickly forming stars that evolve differently than those observed. If gravity were weaker, structure formation might proceed slowly or fail to produce galaxies similar to those in the observable universe. These variations demonstrate the role of constants in shaping cosmic behavior without implying that such conditions exist in any physical region. Another form of variation concerns particle properties. In theoretical models, particle masses or interaction strengths may differ across hypothetical domains. These differences influence how particles combine, how radiation behaves, and how structures form. For example, if the mass of the proton or electron varied, the stability of atoms might change. Atoms might fail to form, or they might form with different energy levels. Such variations show how sensitive atomic structures are to particle properties. By studying these dependencies, scientists better understand the significance of particle masses measured in the observable universe. Variations in nuclear forces also influence cosmic evolution. The strong nuclear force binds protons and neutrons together, while the weak nuclear force governs certain particle interactions. Changes in the strength of these forces alter how elements form in stars and during early cosmic conditions. If the strong force were slightly weaker, many atomic nuclei would become unstable, reducing the number of elements that could form. If the strong force was slightly stronger, nuclear reactions might proceed too rapidly, altering the balance of elements. These variations demonstrate how nuclear physics influences cosmic chemistry, highlighting the importance of measured force strengths. Radiation properties also vary in theoretical models. The speed of light determines how radiation travels across space and how quickly information can propagate. If the speed of light were different, the relationship between space and time would change, influencing cosmic expansion and the behavior of particles. Changes in radiation properties could alter the conditions under which stars form, or how energy moves through gas and dust. These hypothetical variations clarify how radiation influences the evolution of cosmic structures. Mathematical models also consider variations in the curvature of space, which influences how matter moves and how light travels. In the observable universe, measurements indicate that large-scale curvature remains close to flat. Theoretical models allow curvature to vary in hypothetical domains, producing spacetime environments where paths of light bend differently and where cosmic expansion follows alternate trajectories. These models help scientists understand how curvature interacts with matter, density, and expansion rate. Even though such variations do not correspond to observable regions, they reveal how cosmic geometry influences physical behavior. Another type of variation involves differences in initial conditions. The observable universe arises from specific early conditions, including temperature, density, and distribution of fluctuations. Theoretical models explore how changes in these initial values influence cosmic evolution. For example, if early density variations were larger, structure formation might proceed more rapidly, creating more massive clusters or reducing the size of voids. If density variations were smaller, the universe might remain more uniform, delaying or preventing structure formation. These variations demonstrate how sensitive cosmic evolution remains to initial conditions established during early expansion. Though these models explore a wide range of possibilities, they maintain strict adherence to known physical laws. The variations occur only in parameters or initial values, not in the laws themselves, unless explicitly defined by the theoretical frameworks. This distinction ensures that hypothetical domains remain grounded in scientific reasoning. Scientists use these models to identify which aspects of the observable universe depend on particular parameters and which remain robust across a range of values. This approach helps clarify which observations place strong constraints on theory. Theoretical variations also provide insight into stability within cosmic evolution. Some parameter combinations lead to unstable environments where matter cannot form coherent structures. For example, drastic changes in particle masses or force strengths may produce domains where atoms do not exist or where radiation dominates to such an extent that matter cannot cluster. These unstable combinations highlight the importance of measured values in creating the structured environment observed today. By exploring these boundaries, scientists gain insight into the range of parameters that allow cosmic structure to emerge. Despite their usefulness, these variations remain entirely hypothetical. No observation provides evidence for regions where physical constants or particle properties differ. Instead, these models serve as tools for exploring the mathematical consequences of changing parameters. They help refine theoretical understanding and test the robustness of physical laws. Scientists approach these models cautiously, ensuring they remain consistent with all known evidence. As new data become available, these models adjust to reflect improved knowledge. The study of hypothetical variations also informs research on the possible unification of physical forces. Some theoretical frameworks propose that forces may appear different at low energies but unify under extreme conditions. If such unification exists, variations in observed constants might reflect underlying relationships. Although this possibility remains speculative, exploring how changes in constants influence cosmic evolution helps reveal which relationships may hold deeper significance. By examining variations in physical conditions, scientists gain a deeper understanding of why the observable universe behaves as it does. The sensitivity of cosmic evolution to these variations clarifies the role of constants, particle properties, and initial conditions. Although these explorations extend beyond direct observation, they remain grounded in scientific modeling and do not imply claims about unobserved regions. With this layer of hypothetical variation described, the exploration moves inward once more to the mathematical consequences of multiverse frameworks, showing how such theories influence predictions and calculations without asserting physical reality. The inward movement now reaches the mathematical consequences of theoretical multiverse frameworks, a layer concerned not with the physical existence of independent regions, but with how their inclusion in scientific models influences predictions, calculations, and interpretations of cosmic evolution. These consequences arise when theoretical domains, each defined by its own initial conditions or parameter values, are incorporated into equations describing probabilities, distributions, and outcomes within a broader mathematical structure. In this context, the multiverse serves as a conceptual extension of established physics, allowing scientists to examine how different possibilities influence theoretical predictions while remaining grounded in known laws. This layer maintains strict neutrality regarding physical reality and focuses entirely on how models behave when theoretical variations are included. One of the most significant mathematical consequences involves probability distributions across hypothetical domains. In some frameworks, a set of possible conditions forms a spectrum of outcomes. For example, inflation-based models may produce a range of density fluctuations, or a distribution of field values across independent regions. When these models incorporate many such regions, calculations describe not a single outcome but a spread of possibilities. These distributions reveal which outcomes arise naturally from the underlying physics and which require specific conditions. The purpose of such calculations is not to suggest physical existence, but to determine how sensitive predictions are to variations in theoretical parameters. In quantum-based multiverse models, mathematical consequences arise from the structure of quantum states. When the equations describing a system evolve, they produce multiple branches representing different possible results of quantum processes. Each branch evolves independently within the mathematical structure, and the set of all branches forms a comprehensive representation of possible outcomes. This approach provides a way to account for quantum probabilities without collapsing them into a single result. The mathematics ensures that probabilities remain consistent across all branches, preserving the predictive power of quantum theory. These models remain mathematical tools rather than claims about separate physical worlds. Mathematical cosmology introduces another set of consequences when exploring solutions to the equations describing space-time. Each solution corresponds to a possible configuration of the universe under certain assumptions. When multiple solutions exist, scientists study them to understand how changes in curvature, expansion rate, or matter density influence cosmic evolution. These models help reveal which features of the observable universe depend on specific properties and which features appear across a wide range of possible configurations. The study of these solutions remains entirely theoretical and does not imply that each solution corresponds to a physical region. The presence of many theoretical domains in these frameworks affects how scientists interpret statistical predictions. Instead of focusing on single values, models may describe distributions of outcomes across hypothetical regions. This approach helps identify which outcomes appear likely given the underlying physical laws. For example, models may predict that certain density patterns occur more frequently than others, or that certain parameter values appear naturally within a broad mathematical space. These predictions inform scientific understanding of cosmic evolution without implying that multiple domains exist. Another mathematical consequence concerns selection effects. When models include numerous hypothetical regions with varying conditions, scientists examine which conditions lead to the type of structures observed in the measurable universe. This process clarifies which features of cosmic evolution remain robust across many conditions and which require fine-tuning. Although such analysis helps reveal the sensitivity of the universe to its parameters, it does not assign purpose or meaning to those parameters. It simply illustrates the mathematical relationship between conditions and outcomes. Some multiverse frameworks incorporate measures to estimate relative frequencies of outcomes across hypothetical domains. These measures assign mathematical weights to different regions or solutions, allowing scientists to compare how often certain conditions arise within the model. The development of such measures remains an active area of research because assigning probabilities across infinite or extremely large sets of possibilities requires careful mathematical treatment. The purpose of these measures lies in refining theoretical predictions rather than describing physical distributions. Mathematical consequences also appear in calculations involving early fluctuations, when inflation-based models produce a spectrum of possible field values. The distribution of those values influences the predicted pattern of relic radiation. Certain models predict specific features in the statistical behavior of fluctuations, such as slight deviations from a perfectly uniform distribution. Observations of Seebeck radiation can test these predictions. Although such tests cannot confirm the existence of multiple domains, they can confirm or rule out specific inflationary models that incorporate a multiverse-like structure mathematically. Thus, the multiverse concept influences scientific practice through its effect on theoretical predictions, rather than through claims about unobserved regions. In some models, the presence of many hypothetical domains influences how scientists interpret low-probability outcomes. If a model predicts a wide range of possible conditions, then rare outcomes may still appear naturally within the mathematical structure. This perspective helps contextualize why certain measurable properties appear as they do. However, these interpretations remain mathematical exercises and do not imply that hypothetical regions exert influence on the observable domain. They simply provide a framework for understanding how predictions vary with model assumptions. Despite the breadth of theoretical models, all mathematical consequences must remain consistent with empirical data. If a model predicts conditions inconsistent with observed cosmic structure, relic radiation, or particle behavior, that model becomes less viable. Through this process, theoretical frameworks evolve as new observations refine understanding. The presence of multiverse components in a model does not exempt it from empirical testing. Instead, such components must contribute to predictions that can be evaluated within the observable domain. This ensures that even speculative theoretical work remains anchored in measurable physics. The inclusion of multiverse-like structures in mathematical models also highlights the boundaries of scientific inference. When predictions depend on properties of hypothetical domains, scientists must interpret the results with caution. They recognize that certain mathematical features may arise from the structure of the model rather than from physical reality. This recognition helps maintain a clear distinction between theoretical exploration and empirical science. It prevents misinterpretation of mathematical constructs as physical claims and reinforces the importance of evidence-based reasoning. Overall, the mathematical consequences of multiverse frameworks serve to deepen understanding of how cosmic evolution responds to variations in parameters, initial conditions, and physical laws. They help identify which predictions remain robust and which depend on specific model choices. They clarify the relationship between quantum behavior, early expansion, and large-scale structure. Most importantly, they highlight how mathematics can extend scientific inquiry into regimes that remain beyond observation, while preserving strict adherence to known physics. With this layer described, the exploration moves inward to the next domain, where observational constraints define the limits of what can be measured and how theoretical predictions interface with empirical data. The inward progression now reaches the layer defined by observational constraints, the domain in which theoretical predictions must align with measurable evidence. This region does not describe unobserved or hypothetical realms, but focuses entirely on the boundaries set by instruments, physical laws governing the travel of signals, and the interpretive limits of data collected from the observable universe. Within this layer, the multiverse remains theoretical, and only predictions testable within observable space can influence scientific understanding. Observational constraints ensure that any model, no matter how mathematically elegant or conceptually broad, must remain consistent with what telescopes, detectors, and measurements reveal. One of the most fundamental constraints arises from the finite speed of light. Because signals require time to travel, the observable universe encompasses only the region from which radiation has had time to reach Earth. This constraint determines the size of the observable domain and defines the earliest epoch visible through electromagnetic signals. No amount of theoretical modeling can bypass this limit. The universe beyond this region remains unobservable at present. The horizon defined by light travel time thus forms a strict boundary for empirical science. Any theoretical model must match all observations within this domain, regardless of what it proposes beyond it. Another major constraint concerns the expansion of space. As space expands, light travelling toward Earth stretches, shifting to longer wavelengths. Eventually, the expansion can become so strong in certain distant regions that light never reaches the observable domain. These regions remain outside empirical reach indefinitely. Although theoretical models may include such regions, scientific practice recognizes that no direct observation can verify their properties. This understanding helps maintain clear boundaries between testable predictions and theoretical speculation. Instrument sensitivity imposes additional constraints. Telescopes detect only certain ranges of wavelengths and only signals above specific thresholds of brightness. Extremely distant or faint objects may fall below these thresholds, rendering them invisible to current instruments. Even within the observable universe, some regions remain inaccessible because dust or gas obscures light. Instruments must filter or correct for such interference, but some limitations remain insurmountable. As a result, models must allow for incomplete observational coverage. They must also avoid relying on signals that current technology cannot detect. This ensures that scientific conclusions remain grounded in available data rather than extrapolated beyond instrument capabilities. Observational constraints also arise from noise and uncertainty in measurements. Instruments produce data with limited precision, and distant objects often appear faint or distorted. Statistical methods help refine measurements, but uncertainty cannot be eliminated entirely. As a result, theoretical models must account for ranges of possible values rather than single, precise numbers. For example, measurements of the expansion rate include uncertainty ranges, and any theoretical model must accommodate these ranges. This interplay between data and theory highlights the importance of uncertainty in scientific reasoning. Relic radiation provides a comprehensive map of early conditions, but even this map is limited by resolution and noise. Small-scale features may be difficult to distinguish, and some patterns remain ambiguous. These limitations influence how precisely models can be tested. The relic radiation reveals the statistical distribution of early fluctuations, but it cannot provide perfect detail. Theoretical frameworks must remain flexible enough to accommodate these observational constraints. Scientists refine models by comparing predicted distributions with observed ones, but discrepancies may arise from limitations in data rather than flaws in theory. Gravitational wave observations add another dimension to the observational domain, yet they too face constraints. Only the most energetic events, such as collisions between massive compact objects, produce detectable signals. Many gravitational wave sources remain too faint to measure. Additionally, the frequency range accessible to current detectors limits the types of events that can be observed. These constraints ensure that gravitational wave data complement rather than replace electromagnetic observations. Theoretical models must match both types of observations, while acknowledging that many predicted signals fall below detection thresholds. Neutrino observations demonstrate similar limitations. Neutrinos pass through matter with minimal interaction, making them difficult to detect. Only the most intense sources produce measurable neutrino emissions. As a result, neutrino data remains sparse compared to electromagnetic observations. Theoretical frameworks that involve neutrino processes must rely on limited data, and predictions must remain consistent with what little information exists. Another observational constraint involves the interpretation of data across vast distances. Because light from distant galaxies takes billions of years to reach Earth, observations capture the universe at different stages of evolution. This creates a challenge when reconstructing cosmic history. Models must account for the fact that distant regions reflect earlier epochs, while nearby regions represent later ones. The uneven temporal distribution of data influences how theories interpret cosmic evolution. Scientists must ensure that models remain valid across the full range of observed epochs. Constraints also arise from the distribution of matter in the universe. Large-scale surveys reveal the positions of galaxies and clusters, but gaps remain due to obscuring dust, instrument limitations, or incomplete coverage. Surveys across different wavelengths help fill these gaps, but some regions remain poorly measured. Theoretical models must accommodate these gaps and avoid relying on data that cannot be obtained. They must also predict structures consistent with the overall distribution observed across many surveys. Observational limits play a critical role in evaluating theoretical multiverse models. Because regions beyond the observable universe cannot be studied directly, only predictions that affect measurable conditions can be tested. For example, certain inflationary models may predict specific patterns in relic radiation. If observations match these predictions, the models remain viable. If not, they require revision or rejection. This constraint ensures that multiverse-related models remain connected to empirical science rather than drifting into speculation. Theories must provide testable predictions within the observable domain to remain scientifically meaningful. Even when theoretical models propose a wide range of possible physical conditions, the observable universe demonstrates only one set of values. These values constrain which models remain consistent with evidence. If a model predicts conditions incompatible with observed physical laws or cosmic structure, it becomes less viable. This process of eliminating inconsistent models helps refine scientific understanding. Observational constraints thus guide theoretical exploration by limiting acceptable parameter ranges. Recognizing the limits of observation also clarifies where theory must remain cautious. Predictions about unobservable realms cannot be confirmed or refuted through empirical data. Consequently, they remain outside the domain of scientific conclusion. Scientists may explore these ideas mathematically, but they must avoid assigning physical significance without evidence. This clear boundary maintains the integrity of empirical science. With observational constraints defined, the inward progression reaches its final theoretical layer. The open scientific questions that remain within the study of cosmic evolution and multiverse theory, questions shaped by evidence, limited by observation, and guided by the boundaries of scientific practice. The progression now reaches the innermost theoretical layer, the open scientific questions that remain within the study of cosmic evolution and multiverse theory. These questions arise naturally from the limits of observation, the structure of mathematical frameworks, and the uncertainties inherent in early cosmological processes. They belong entirely to scientific practice, reflecting areas where evidence is incomplete, models remain under refinement, or measurements have not yet achieved sufficient precision. They do not imply conclusions about unobserved realms. Instead, they clarify what remains to be understood within the boundary of empirical and theoretical cosmology. One of the central open questions concerns the exact nature of inflation. Although inflationary models align with many observations, the specific mechanism that drives rapid expansion remains uncertain. Scientists continue to investigate which field or combination of fields may have produced the energy necessary for inflation. Different models propose different behaviors for this field, leading to variations in predicted fluctuation patterns. Observations of relic radiation help distinguish among these models, but no definitive identification has yet emerged. The uncertainty reflects the difficulty of probing conditions that existed at extremely high energies and very early in cosmic history. Another open question involves the exact distribution of primordial fluctuations. Although measured patterns align with quantum predictions, slight deviations may reveal more about the processes that governed early evolution. Scientists search for signatures of gravitational waves imprinted in relic radiation, which would indicate specific properties of early fluctuations. Detecting such signatures would refine understanding of inflation and could help constrain theoretical models. The absence of a confirmed signal does not disprove these models, it simply reflects the sensitivity limits of current instruments. As observational techniques advance, new data may clarify whether such signatures exist. The behavior of dark matter and dark energy also represents a major open question. Dark matter influences structure formation through gravity, but has not been detected directly. Its particle properties remain unknown, and various theoretical frameworks propose candidates. Observations of galaxy motion, gravitational lensing, and large-scale structure provide indirect constraints, but they cannot fully determine its nature. Dark energy, which influences the acceleration of cosmic expansion, remains even more mysterious. Its behavior shapes the long-term evolution of the observable universe, yet its physical origin remains unclear. These uncertainties highlight areas where theoretical and observational research continues actively. Quantum gravity forms another boundary where open questions remain. Gravity and quantum mechanics both describe essential aspects of the universe, yet no single framework successfully unifies them across all regimes. The behavior of gravity at extremely small scales remains unknown. This gap influences theoretical models that describe early cosmic conditions where quantum gravity may have played a significant role. Different approaches propose various solutions, but no empirical evidence currently selects one model over others. The development of a coherent theory of quantum gravity would significantly enhance understanding of early cosmic evolution. The distribution of physical constants across hypothetical domains also raises scientific questions. Some models allow these constants to vary, yet the observable universe shows no evidence of such variation. Scientists continue to measure constants with increasing precision to determine whether subtle changes appear across large distances or over time. So far, all measurements indicate uniformity. Whether this uniformity reflects a deeper principle or simply a property of the observable region remains unknown. Clarifying this issue may require more precise instruments or new theoretical insights. Another open question concerns the possibility of detecting indirect evidence of theoretical multiverse models. Although direct observation remains impossible, certain predictions may influence measurable properties of the observable universe. For example, some inflation-based models suggest that interactions between regions during early expansion could leave imprints on relic radiation. Scientists search for unusual patterns that may indicate such interactions. No such patterns have been confirmed, but ongoing research continues to examine relic radiation for subtle signatures. Any detected deviation would require careful interpretation to distinguish between instrumental effects, astrophysical process, and theoretical implication. Open questions also arise from the limits of observational data. Although current telescopes survey large portions of the universe, many regions remain unobserved or poorly measured. Improvements in sensitivity, resolution, and wavelength coverage may reveal structures or behaviors not yet known. For example, deeper surveys of distant galaxies may clarify how structure formation proceeded at early times. Improved gravitational wave detectors may reveal previously undetectable events, offering insight into the behavior of massive objects across cosmic history. Each new measurement contributes to refining or revising theoretical models. Uncertainty also surrounds the future evolution of the universe. Although current data suggests that expansion continues to accelerate, the long-term behavior of dark energy remains unknown. If dark energy changes over time, the future trajectory of expansion may differ from current predictions. Models explore various possibilities such as gradual increases in acceleration or transitions to different expansion regimes. Observations across multiple epochs help constrain these scenarios. but the long-term behavior of dark energy remains open. This uncertainty highlights the limits of extrapolating from present data to distant future conditions. The relationship between quantum mechanics and cosmology also presents open questions. Quantum fluctuations play a central role in early evolution, yet the interaction between quantum processes and large-scale expansion remains incompletely understood. The precise mechanism by which fluctuations become imprinted on space, the role of coherence in early fields, and the transition from quantum uncertainty to classical structure formation remain areas of active research. These questions lie at the intersection of quantum theory and cosmology, where further theoretical development may shed light on underlying processes. Scientists also continue to study how well current models represent the earliest measurable moments. Some theories propose modifications to inflation alternative mechanisms for generating fluctuations or new interpretations of relic radiation. These proposals remain speculative until supported by data, but illustrate the ongoing effort to refine understanding of early cosmic evolution. Research in this area often seeks to resolve tensions between different measurements, such as small discrepancies in parameter estimates derived from various observational sources. These tensions may reflect measurement uncertainty, or may point towards the refinements needed in theoretical frameworks. Despite the presence of these open questions, the observable universe remains well described by established physical laws and supported by a wide range of measurements. The areas of uncertainty provide opportunities for further research rather than contradictions of known science. They represent regions where knowledge remains incomplete, where models require refinement, or where improved instrumentation may reveal new insights. These questions define the frontier of cosmology and guide future exploration within the boundaries of scientific inquiry. With all layers of the exploration completed, the narrative now shifts from theoretical domains to the calm closing of the journey. The wind down returns gently to the observable universe, settling into a steady and restful tone that reflects the continuity of cosmic evolution without offering interpretation or meaning. The narrative settles back into the familiar quiet of the observable universe, where light travels across great distances and carries traces of ancient events through the vastness of space. The journey through outer layers of cosmic structure, early evolution, theoretical extensions, and scientific questions gives way to a gentle return to the present moment in which the universe continues its steady expansion. Galaxies drift across time, shaped by gravity and by the distribution of matter established in their earliest stages. Their light moves outward through space, crossing regions of dust, gas, and dark matter before reaching instruments designed to measure faint signals. Each signal reflects conditions that existed long before the present, allowing scientists to reconstruct cosmic history through careful observation. The relic radiation remains a constant presence, filling space with a glow that carries the imprint of early fluctuations. Its temperature varies by amounts too small to sense directly, yet these variations reveal the earliest structures capable of influencing cosmic evolution. As instruments observe this radiation, they trace patterns formed when the universe was young and expanding rapidly. These patterns align with the predictions of established physical laws, providing a foundation for understanding how the observable universe emerges from earlier conditions. The steady background continues to cool as expansion proceeds, offering a quiet reminder of the passage of time across billions of years. Stars form within clouds of gas shaped by gravity and turbulence. Their light reflects chemical elements created within earlier generations of stars. These elements disperse into surrounding space when stars complete their life cycles, enriching the medium from which new stars and planets emerge. This ongoing process unfolds gradually across galaxies, influencing their structure and brightness. Observations of these processes help clarify how matter behaves under changing conditions, providing insight into the long-term evolution of cosmic environments. Galaxies cluster together, forming patterns that extend across great distances. The arrangement of these clusters reflects the early distribution of matter amplified by gravity. As scientists measure the positions and motions of galaxies, they reconstruct the large-scale structure of the universe with increasing precision. These measurements confirm that the observable universe evolves according to known physical laws guided by gravity, radiation, and the properties of matter. Even as uncertainties remain about aspects of early evolution or the nature of dark components, observations provide a stable framework for understanding how galaxies form and change over time. The expansion of space continues, stretching distances between galaxies. This expansion influences how light travels and how structures evolve. Although many questions remain about the properties of dark energy, the observed acceleration of expansion provides clear evidence that cosmic behavior changes across time. As instruments measure this expansion at different epochs, they refine understanding of how the universe grows. The steady increase in distance between galaxies unfolds without haste, marking one of the defining features of the large-scale environment. Within this calm cosmic setting, the observable universe presents a consistent and measurable domain in which physical laws operate uniformly across vast distances. Matter follows predictable paths shaped by gravity. Radiation travels according to well-established rules. Quantum processes unfold at the smallest scales, influencing particles and field with precision. These processes combine to form the structures and behaviors measured across the sky. The continuity between microscopic and macroscopic behavior provides a stable foundation for understanding the universe without extending beyond the limits of observation. The open questions that remain do not disturb this steadiness. They simply point toward regions where knowledge grows as new instruments detect fainter signals, measure finer details, or observe previously unseen environments. The quiet progress of scientific inquiry continues, guided by the measurement analysis and evidence gathered from many sources. Each improvement refines understanding while leaving space for future discoveries. As the journey draws to a close, the vastness of the universe remains unchanged, stretching outward through distances beyond measurement. Galaxies continue their slow motions, stars continue to shine and fade, and radiation continues to travel across space. The calm patterns established over billions of years persist, shaped by predictable forces and consistent laws. The observable universe remains a steady and measurable environment, offering a quiet backdrop against which scientific exploration unfolds. In this stillness, the narrative rests, allowing the mind to drift through the gentle continuity of cosmic evolution, unhurried and unbroken. The universe moves forward without haste, carrying traces of its earliest conditions into every corner of space. Its light travels onward across great distances, soft and steady as the night deepens and the stars remain.